So what I made myself a note card because I knew that there was no way I would remember this. According to my note card or my sticky note here, on Thursday before we parted ways, we had started our second example and that we had just factored it, and that was the end of it. So let me get that copied back up here. So the function was f of x equals x cubed plus x squared minus 12x. And according to my records, we had factored. So we're going to pull out an x, and that's going to leave us with x squared plus. Thank you very much, Erica. So there's an x here. So we're going to pull out the x, and that's going to leave us with x squared plus x minus 12. Bless you. And then we're going to complete the job by saying x times x plus 4 times x minus 3. So is this about where we got to? Okay. So one of the things we talked about was finding the zeros. That really should be the first place we always go, is to find the zeros, the crossing points. So what would we say then are the zeros of this function?
Negative.
There are going to be 3 zeros, actually. So we get one of them from the red factor, and we get one from this first factor. You're going to have to tone that down, buddy. You're going to have to, are you done with that? Thanks. And then over here, we have another one. So what do we get from the red factor? No, it's funny the things people say. That's the easiest question that I clearly don't understand how to ask, because it's not you, it's me. You've heard that before. What makes the green box equal 0? What's the only number you could put in place of that red X to make the contents good? The answer is 0. Anytime you have a GCF like that that contains a variable, one of your zeros is going to be 0. Got it? It's the only number that can make a GCF go bye-bye. And then what number or 0 do we get from the second, from right here? -4, good. And then the third is at 3, good. So one of the things you'll be asked to do in your worksheet is just make a sketch. And your sketch does not have to be a work of art, so I'll just kind of show you what my expectation would be. Just put a little x-axis and a y-axis, and let's mark those spots on the x-axis. And so I'm going to put some red dots where I think those would be. Let's start with 0. There's a crossing point at 0. Another one is at -4, and that's like right here. And then the other one is at +3, so we can put that like right here. Got it? Still so far so good? Okay, so this is where end behavior comes in to save the day. We talked about end behavior, and because this number, follow the purple arrow up here, because where I'm pointing, there's a positive number 1, and because of what I'm circling in purple is an odd number, what does positive odd tell us about end behavior? Good job, Mason. It starts down and it ends high. So in light of that knowledge, it has to start over on this side like this, and it has to end on this side like this, right? That's where end behavior bails you out, as it tells you now structurally the graph can only exist in one logical way, right? So if we continue the graph, it has to come up like this, it has to swoop back down like this, and then it's going to swoop back up like this. So end behavior to the rescue. It tells us structurally how the graph has to look, like literally has to look. There can be some nuancy differences as to how tall it goes, but that's not, again, that's in calculus, you'll study finding these points right here. These are extremes, extrema, like that's a relative maximum and that's a relative minimum. And so we're not going to probably talk too much about that, but we're just interested in the zeros and the behavior of the graph in general. So how many intervals do you see on this graph? 4. I see 4. Good job. So I'll color code them for you. There's this green interval right here. There's going to be a yellow interval right here. There's going to be a purple interval, which I guess I don't have to change, but I will right here. And then, of course, there's this red interval right here. So we agree that the intervals exist as defined by the zeros, right? So how could you define for me the green interval? So the green interval, we can say the function is negative when what? When x is less than what? -4. Very good. Got it? The function is below the x-axis if your x value is to the left of -4. If you're anywhere on the x-axis at -4.1 or -62 or something, your graph is below you. How would we define the yellow interval? It's positive when good job. And so I have to find a way to say, and when I did get one of these into the notes quickly, I think I have to find a way mathematically to say that it's bigger than this and also less than this. And the way we do this is we put X in the center, and then we put two Pac-Mans both facing to the east like this. And I'm going to show you a better, different way to express an interval at some point today, quickly. But in the meantime, that's how you set up a between interval. And then I simply have to put the boundary, the starting and stopping points to the left and the right of the Pac-Mans. And so this interval starts at -4 and it ends at 0. Okay. That's called inequality notation for an interval. And again, there's a better way, but we got to get them both. So we'll get the poopy one done first. Next up, in order, should always work your intervals, by the way, from left to right. There's no sensible reason not to. So we're going to head to the right now, and our third interval is the purple one. And what would we say about him? It's negative when good job. And so again, because it's a tweener, it's not a start and go forever interval. I'm going to stick my X in the center, put two Pac-Mans both facing to the right like this. And again, like Seth said, it goes from 0 and it caps or ends at 3. And then my final, remember, is an unbounded interval that goes forever. So this one, I don't need two Pac-Mans. I'm just going to say for my last interval that the function is positive when what? More than 3. Good. And this answer brought to you by the sketch of the graph, right? Sketch of the graph gives us what we need to see about when are you down and when are you up. So any questions on that? All right, let's do another. There's a fly on my computer screen. Step 1. GCF, yeah, factor. I'm glad to hear you guys. You just jumped all over that. Good job. You attacked the sport problem. So we can pull out an X, and what does that leave behind? Plus 13X minus 10. So I'm still in factoring mode here, but this ain't our first rodeo. So we know to build the two shells, to stick in a 3X and a 1X. We know there's one positive and one negative, right? And I feel like the logic of it is to put the 5 over here and the 2 over here. Because of course they make 10, but more importantly, by powering the 5 up with the 3, I get a 15, and then I take away the 2. So I want the positive on the 15 and the negative on the 2, right? So how many zeros will we get from these factors? 3. Each factor will produce a 0 until they start becoming quadratic factors, and then we'll have that conversation later. So linear factors produce 1 each. So the red factor produces a 0 of, well, 0. What does the first parenthesized factor give us? Nice job, Sutter. 2/3. Right. How about the last factor? Good job, you guys. So the zeros pop out of the factors. The factors exist to give us zeros. That's now, surprise, that's their role in mathematics, is to expose those little crossers. And so we're going to make a sketch. Just a quick one, just x-axis, y-axis. And again, the sketch isn't gorgeous. It's just to give us what we need. We're just only after one thing, and that's the behavior of the graph. So we're going to stick one at 0. We're going to stick one at -5. And then we're going to stick one at 2/3, which honestly is going to be really tight in there like this. And so again, without end behavior, we don't really understand how the graph behaves. But look back to the original function. What is his end behavior? Down and then up, right? So it's again, a positive intro number and an odd power, so down, up. So I know my graph is going to end over here, down, and over here, up. And that's all I need. And then I can, again, just make a sketch like this. And that graph, I'm sure, balloons much higher than my half-hearted sketch shows, but that's okay. So I'm sure this mound right here is much higher. If we were to graph it on Desmos, you would see that. Good. Okay, this time I want to do this, but I'm going to show you a different way to do notation. I'm going to show you something that if you plan on taking more math classes, A, you'll really appreciate, and B, you're going to use it a lot. So I'm going to show you in this one interval notation, which is fantastic. So here we go. Let's get started with our first interval, and I don't really want to color code them again if it's all the same to you. Let's start with the first interval that we encounter, and that's that first one coming in from the left. So I'm going to show you, I'm going to write this down. I'm going to say that this graph is negative when, ready? Trust me, you won't like it for the first minute and 12 seconds, and then you will. It's better because it saves us having to write inequality signs. So what that is an interval that says that from negative infinity to -5, that means as far left as you could possibly imagine until you get to -5, the graph is negative. Okay, it looks like an ordered pair, like how we do X's and Y's, but anyone reading that would understand that that's, oh, they're defining an interval. Okay. Let's go again. My next interval as I go from left to right is positive when, and again, I'm going to use my interval notation. And what does it go from? -5. So I can just put -5 to 0 like this. You would look at that again and think it's a point, but you have to think in, just like when you read English, you have to think about context, right? The grammar, the English, the sensibility of it wouldn't make sense if someone said positive when ordered pair negative. What that didn't even make sense. So that's an interval. Let's go again. Our third interval is negative. And what can we say about that? Negative when from 0 to 2/3. And then our final interval is positive when. So we go from 2/3, comma, to positive infinity. Good. And you can put the positive sign or leave it off. Everyone knows by default that it's positive. The one thing I want to say so that Mrs. Eklund doesn't come back and say, what did you teach those poor kids? Is that with intervals, you'll sometimes see this notation. So like if I put this square bracket and I put like from 4 to infinity, this means that 4 is included. So when we use interval notation like this, we won't have a lot of opportunities for it in the next couple of days, just the context of what we're doing. But if you put a square bracket, it means that that point is part of the interval. But why am I not including my points in my intervals? Like, for example, why is -5 not in the interval where it's positive from -5 to 0, Sutter? Because it's on the line, right? And so if you're on the line, if you're one of those three crossing points, your function's value at that point is neither positive nor negative, right? You agree? So that's why we're using rounded parentheses for that interval, because those points are not part of the intervals. So the square bracket will come in when we want to include points in our intervals. You can use this notation if you'd like. You may also use the inequality notation if you're weird, if you're one of those weirdos. So good. Let me see if there's anything I can skip. I think I can skip that one. Let's do this one. I'm going to knock a couple out because I feel like you're probably doing okay. Let's do f of x equals -4x cubed minus 16x squared plus 20x. And that'll leave us with just 2 more, both of which have a very specific purpose. So I'm not going to kill 6 or 7. I did kill 4. So, all right, step 1. Pop out that GCF, which is what? -4x. Good job. So we know already that he's going to give us one of our answers, right? Predictably, we're going to have a crossing point at 0 again because of the GCF. And then what does that leave behind? Yeah. Good job. Good sign switching. And then, of course, we're going to factor down that little rinky-dink trinomial into x plus 5 times x minus 1. Right? So what are my zeros? First one? 0. Right? Take that. Run. That's a freebie. Second one? -5. And the last one? +1. Good. So again, the purpose of the graph, we're not doing a unit right now on graphing polynomials so much. I just need, again, the sketch so that I understand the behaviors, where the intervals are up and down. So I'm just going to make a quick sketch. X-axis, y-axis. Doesn't have to be nice or beautiful. My crossers are going to be at 0, -5, and +1. So what is the end behavior of a function like this that has negative odd? Up, down. Good job using your resources. If you're looking at your notes, great job. If you've already memorized that, great job. But either way, awesome. So we know that it's going to start high, do its thing, and then end low, right? So the graph comes in from the east or from the west on the high like this, and it will exit on the east on the low side like this. And that demonstrates for us what the graph now has to do. It has to dip down like this. Oh my God. And then it has to come back up like this, and then redip and go forever like this. And that's all the information that I need to get through what I need to get through. I got my zeros, got my end behavior. Now I just need to describe the intervals. So left to right, always, please, 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 left to right. What's the first interval, would you say? So we can say that the graph is positive when what? Good. So from -infinity to -5. By the way, infinities will always have the exclusive bracket, the round one. You'll never, even if you take 5 years of college math, never will you put a square bracket on a positive or negative infinity. You can't include infinity, so that's why it's always rounded. What's my next interval? That's this guy, second. Negative when? Good, so from -5 to 0. Next one, positive when? 0 to what? 1, good. And then negative when? 1 to infinity. Okay, I have 2 more examples, and they each just serve a purpose, not so much now in the concept of how to do it, but just more in the different types of factoring that you potentially could see. So let's get to it. And we honestly might not even finish this one. We can if you want to, but what I more just wanted to show you is just the front end of it, that they're not all going to be the same factor-wise. So we have f of x equals x cubed minus 3 x squared minus x plus 3. What do we do first? Yeah, it warms my heart when you say stuff like that. GCF. That means you have learned well. What's the rub here? What's the trouble? There isn't one. So I better have a plan B. What do you think it is? Build your wall. Good job. You guys are amazing. This looks like if it's factorable, if I was meant to find zeros, I'm going to do it through grouping here. So I'm going to wall down the center. And now I am going to do the GCF, but only of the front end. What's the GCF of the front end? So x squared, leaving behind. Nice job. And then on the right-hand side, and what's the GCF? 1, leaving behind. Good job. So at this point, if this were just on the last quiz and it were just a factoring problem, my answer would be x minus 3 times x squared minus 1. And of course, if I turned it in like that, I would get a big downward arrow with a question mark and the infamous -2 because you didn't finish the problem. What did I miss? There's a difference of squares just staring right at me. Dare I say it's staring squarely at me? What would the zeros be in this case, you guys? And x would equal, and x would equal. Yeah. And then from there, you would mark them. Do you feel like we're okay if we don't do that part of it? Do you, we can if you want. Do you want to keep going? Do you understand that we graph the zeros and then we use the end behavior to guide us as to how the curve goes? Is everyone okay with that?
Yeah.
Okay. Let's bypass then the rest of that and let's get to the final example and then I'll let you work. So this function is f of x equals -3 x to the 4th minus 6 x to the 3rd plus 12 x to the 2th plus 24x. What do we do first? Yeah. And what is the GCF?
4x.
It is -3x. Perfect. First, pull the negative just because the first guy has one. Then pull the 3 because they all can be divided by 3. Then pull an x. And then that leaves us with the actual factoring problem, which is what? Yep. Yeah, well done though. Well executed. All of that was really good. Okay. This one we are going to see through to the end because it'll have a different end behavior than its predecessors. So yeah, so now we're going to remember kind of put the GCF out of sight, out of mind for a little while, and then we're going to wall down the center right here. What's the GCF of this left half over here? X squared. So I'm going to pull x squared, and what does that leave behind? Then I'm going to drop the minus, and what's the GCF? Bless you. 4, leaving behind. X changed the sign to, right? And then we see the match. So we know grouping was successful. So our current state is we have, here we go, GCF times commonality, x plus 2, times stuff we pulled out in the process of grouping, x squared minus 4, like this. We done? No. That difference of squares, that quadratic factor is going to produce more factors, which will then produce the roots, so the zeros. So we have -3x times x plus 2 times x plus 2 times x minus 2. Good? Okay, so now we're going to, this one, I don't know if I did this on purpose or not. I wrote these like 5 days ago, but something interesting is going to happen. So we need graph, we need axes. So we have a y-axis, we have an x-axis. And I will rely on Desmos to help me. Inevitably, what I'm about to try to explain is going to fail. Oh, it probably will. Not to be negative, but yeah. So I'll head over to Desmos when I'm done and see if that will help this click. So I'm going to find some zeros first off. So what 0 do we get from here? X equals what? 0. Very good. Always remember your GCF is going to give you 0. It's the only thing that can make a chunk of junk equal 0 is a 0. When it's a chunk of junk, it's a 0. What do we get from here? What do we get from here? Okay, that's going to be important. And what do we get from here? Good job. So we're going to go through and we're going to mark these, and hopefully you learn something from this. So 0 gets a mark, -2 gets a mark, and +2 gets a mark. So first off, let's talk end behavior. Go back to the beginning of the problem and let's talk about the end behavior. What would we say? What did our notes tell us when it's negative even? Down, down. So this could really hurt the brain. If you know the end behavior is down, down, then that means that when we come off of this left arm, that it's going to go down like this. And it also means that when we come off of this arm, it's going to go down like this. Right. And if you try to sketch this graph now, your brain is going to explode because logically it can't work. So like follow along with my fails here. If I try to come up like my teacher taught me and come down, then you realize, Houston, we have a problem, because then logically it's going to go like that, right? And of course, there's an explanation for this, and this will be the last thing I try to teach you. And if this goes well, you can give me like a thumbs up or something like that. Really important. Really important. You guys notice that this 0 occurred twice? Ready? Because it occurred twice, it's what we in math land call a bounce root or a bounce 0. When a 0 occurs twice, it does the work of 2 zeros, and the graph does not cross through the axis at that point, but it bounces off. Meaning that this root right here actually does not cross. It's like you ever seen those planes like at the air base when they come in and they touch down and they go right back up? It's like that. So the graph with this, by the way, is called multiplicity. That 0 has multiplicity of 2, which gives it that bounce effect. And now the graph makes perfect sense. And you're like, oh, I see. Because you're a bounce root, then you come down, you bounce off, you go back up, and then you get the McDonald's purple arches like that. How many intervals do you see? Yeah, I see 4. I see a negative, a positive, and then a negative, right? So let's finish this, and then I'm going to go head over and let you see it on Desmos, like an actual graph of it, and then I'm done. So my first interval is this yellow one, and we can say that that interval is negative when what? From negative infinity to negative 2. Good. Now my second interval, I'll make it red. It's right here. And we say that that is positive when what? From negative 2 to 0. Why can I not make the red and the green just into one positive interval, guys? But why can't I just say that the graph is positive? Screw it. I can just positive from negative 2 to 2, right? Because 0 is not positive, right? So it's broken. There's 2 intervals, and we have to respect that by saying there's a point in the center where that's not true. So we define it from the left, and then we define it on the right. So we also have another positive interval when we go from 0 to positive 2. And then finally, we have, I'll do, I guess, purple. Don't change this one. We have a negative interval when what? Good. So I'm going to head over to Desmos real quick. Everybody got that written down? So open up a new tab, go to Desmos, graphing calculator, and I'm going to type in that function, which was negative 3 x to the 4th minus 6x to the 3rd plus 12 x to the 2th plus 24x. And that.
You bounce on the 2, not the 0.
Did I put a bounce root at 0?
Yeah. Yes. That's what I was confused about.
Oh, don't mind your teacher. Gosh, well, I'm glad I got that on recording. Geez Louise, what was I? Why would I do that to you? Why did I bounce at 0? What a crackhead. Let me start over. No, that graph was terrible. I was going to just make a joke, and then I realized I shouldn't make jokes like that on video. So that joke, that joke, nope, that joke's staying on the inside today, kids. Yeah, that is completely and totally sorry for that. That is terrible, but I'm glad that you guys get to see me make mistakes too. So let's put our zeros back on. So we have our 0, we have our negative 2, and we have our positive 2. And I, like a moron, put the bounce at the wrong place, of course. So the bounce occurs at negative 2, but we do understand still what the end behavior is, right? The end behavior is non-negotiable. So the graph is low and the graph is low. That's not up for debate at all. So yes, the bounce occurs right here, right? And then we get a slash through this one, and then a slash through this one. So apologies for that. Thank you. You could have said something, but you also probably maybe thought I knew what I was doing, which you'd like to think that I do. So that's what the graph should look like. And again, what you find is we may understand the behavior and how the graph kind of dipsy-doos, but what we can't account for with these like rudimentary sorts of understandings is we can't account for how extreme it is. You see how high that graph goes? It peaks out at almost 30. And my little sketch doesn't really do that much respect or justice, right? So good. I'll just leave the screw up on the recording. That'll be good for if anyone watches it. Hopefully they watch all the way to the end though to know that I was false information. So how do you guys think you're okay with this? All right. I don't know if you'll see any bounce roots, but if you do, try not to screw them up like I did. Do better. Do more gooder than I did, kids. I think the assignment is on Canvas. Has anyone looked by chance? If it's not, I will put it up there right like now-ish.
Right.